let's make a start then. Implicit differentiation. All right, so implicit differentiation is a method where if you've got some function that's not in the form of y equals, then we use implicit differentiation. Too many wiggles in there. So implicit differentiation is used when a function is not in the form y equals. Alright, so it saves us having to rearrange it. And in fact what it is an application of the chain rule. And in this example, I've got a few examples, but in the first example, I'll show you how that chain rule fits in. So this first one, so we're going to differentiate y squared plus 2x equals 3 to find dy dx. Alright, so it's not written in the form of y equals. We could rearrange it. This particular one's not too difficult to do that. Other functions might be more complicated and more difficult. Alright, so effectively what I'm going to do is I'm going to differentiate that stuff. Alright, so if I then split it into the three bits, we're going to differentiate y squared with respect to x. We're going to differentiate 2x with respect to x, and we're going to differentiate 3 with respect to x. So with these, the last two, the d dx is straightforward. The differentiating 2x with respect to x, that's straightforward. But here, we've got y squared, and we're going to differentiate that with respect to x. So for this bit here, this one here, this is where our chain rule comes into it. And so what I'm going to do is we're going to split that up so the derivative of y squared, because it's y squared, that's where the complication comes in. This is where we're going to put the chain rule. So I'm going to differentiate y squared with respect to y, but then I need to multiply by dy dx. So, excuse me, this is where our chain rule comes in. And it's because we've got y squared here. If we just had straight y, then we wouldn't have to worry about using the chain rule, but because it's y squared, and we can't, well, as far as x is concerned, y could be a number, but we we know y is not, so we can't differentiate y itself with respect to x. So we've got to split it up and differentiate the y squared with respect to y, but we've got dx that we want on the end, so we multiply by dy dx. Right, any questions about that aspect? Because this, in terms of the implicit differentiation, this bit here, that's the key to it all. All right. Okay, so when we differentiate, so then I've got y squared times dy dx plus the derivative with respect to x of 2x plus the derivative with respect to x of 3. Alright, so if we're differentiating y squared with respect to y, what do we get? 2y, yep. So then we've got 2y times dy dx, which is what we're after in here as well, plus, when we differentiate 2x with respect to x, we get 2, and when we differentiate 3, we get 0. So we've got 2y times dy dx. I'm going to take 2, then going to divide by 2y, and you get negative 1 on y. Alright, so differentiate y squared plus 2x equals 3 to find dy dx. So we've now found dy dx is negative 1 on y. And if we have got a sum that we're doing, finding a gradient or something like that, then this y is the y value. And I'll do an example of that. Now your calculator. I've been accused of not showing people how to use the calculator. Terrible. So your calculator can actually do implicit differentiation, but before I get to that, in the Math 2 tab, these 3 things here, that one, that one, those two can do differentiations, and this, when we get to it, can do integrations. Alright, so you can do that in your calculator, and on the SAC there'll certainly be parts on our SAC that you'll use the calculator for. Won't be doing it all by hand. However, implicit differentiation. So if you go action, calculation, a whole bunch of stuff here. Second one on the left, imp diff. If we imp diff y squared plus 2x equals 3, then we get y dashed. So y dashed, which is dy dx, equals negative 1 on y, which is what we got there. Alright. Alright, let's do a couple of examples. Which are a bit more involved. Alright, so So differentiate 2xy squared equals x minus y, giving the answer in terms of x and y. Alright, just notice I haven't written down, it is that it's differentiated with respect to x. I didn't write that in the example, which I should have. But looking at my working there, that's what I've done. So we've got to differentiate this with respect to x. So we've got three parts. We've got the 2xy squared, we've got this x term and the minus y term. So if I differentiate each of those terms with respect to x, and minus y. Okay.
So you differentiate all with respect to x?
All with respect to x. They would all with respect to the same one. Yeah. All right. Now, in this particular one, again, the right-hand side here is pretty straightforward. Differentiate that, you get 1. This is simply just dy dx. But here we've got something extra because we've got 2xy, we've got 2 times x times y, and then we've got not just y but y squared. So this term here is the one that we need to work a bit more with. Now, because this is, we can say that that's 2x times y, we now need to also use the product rule here. All right, so product rule, if I make 2x equal to u and y squared equal to v, so it's u times the derivative of v plus v times the derivative of u is our product rule. So if we do that, and I'm going to differentiate this, so I've got u times the derivative of v, and I've said u is 2x, so I've got 2x times the derivative of v, and v is y squared, and v is y squared. Yes?
Yep.
Plus v, and v is y squared, times the derivative of u, and the derivative of 2x. Oh, I'll just write it down without doing it at the moment. All right, that's that side, yes? Equals derivative of x with respect to x is minus dy dx on the end. All right. So again, now we've got our technique that we used in the previous example, because we've got this y squared one, yeah? So 2x times, oops, not 2 times, 2x times. So 2x times All right, dy of y squared times dy dx. All right, that's that chain rule implicit differentiation technique. This one here, well, y squared, it's 2x, it's being differentiated, so it should be just times 2. And we've got that. Yes? No? Yeah. Happy with that so far? All right, let's all of this stuff here. Now, so we've got all of this stuff we need to neaten up. So 2x is still 2x. If we differentiate y squared with respect to y, we get 2y. And dy dx is dy dx. And we've got 2y squared here, 1 minus dy dx. And if I put all of this, still need to neaten that up a little bit. 2x times 2y is 4xy times dy dx plus 2y squared equals 1 minus dy dx. Alright, now what? Any suggestions? Anyone? Bright ideas? No one got any bright ideas? Well, this has got dy dx in it, and so does that. So how about we move this one over this side? And then, of course, this term here doesn't have any dy dx's in it, so how about we stick that over that side? Alright, so effectively we're kind of getting our like terms together in a sense. Alright,
You
so
take 4xy over as well?
oh, it's already on the left, I'm going to leave that. Because
Yeah.
that's multiplied by this dy dx.
Yeah, no.
So I'm going to leave that there. Oops. Going to leave that there. Bring this one across. And I'm going to take that one over there and leave this one here. Alright. So we've got 4xy dy dx. Then when I bring that other one, I've got to add it. Got that one that was there already, that's still staying there, and I'm moving my 2y squared. When you do that, I've got to take it. Now, what do you notice? Anything? Would they or would they not be a common factor? They're common to each of those terms, aren't they? So we take it out as a common factor. First term here we've got 4xy. There's one of them. Divide both sides by. That bracket. Dy dx then is 1 minus 2y squared over 4xy plus 1. Right, anything you want me to clarify about that? No, nothing, just got to get it straight in your head. Let's do another example. Alright, so say for example you're wanting to find the gradient or a tangent or something like that. Right, you don't have to have it form y equals, you can do this implicit differentiation, and you can do it. Like if you wanted at a point, a particular point that was on that curve, initial curve that I've now rubbed out, you would have an x value and a y value, and then you would just substitute those numbers into there to find the gradient at that point. So that's what we're going to do now. So for this one's x squared plus y squared plus y equals 2. Find the gradient of the tangent. Actually, I've made a mistake there. It's not x squared plus y squared, it's x squared times y squared, sorry. Point 1, negative 2. Alright, so if we're wanting the gradient of the tangent, so the gradient of the tangent is the same as the gradient of the curve at the point, and the gradient of the curve is dy dx, is correct? Yes?
Yeah.
Alright, so we need to differentiate x squared plus y squared. Plus, done it again, x squared times y squared, not x squared plus y squared. X squared times y squared with respect to x, y with respect to x, and 2 with respect to x. Alright, so again, with this first term, got the same sort of thing as we had in the previous. We've got two things that are multiplied together. So we need to use our product on that. So again, if I'm saying that that's u and that's v, so the product rule says u times the derivative of v, so that's x squared times the derivative of y squared, plus v times the derivative of u, so that's y squared times the derivative of x squared. Yes? Happy with that? Then the next term, the plus dy dx, is just plus dy dx. And that equals 0, yeah. Alright. So this bit here, this when we're differentiating y squared with respect to x, that's where we do that funky chain rule thing again, which says x squared times the derivative with respect to y of y squared times by dy dx. Alright, plus I've still got y squared here, timesing it by the derivative of x squared is 2x plus dy dx equals 0. Alright, some more stuff. That's this first term, let's neaten it up. So I've got x squared. When I differentiate y squared with respect to y, I get 2y times that dy dx that's there, plus 2xy squared plus dy dx equals 0. Alright. So this is now where, like I did before, we want to get our terms with dy dx in them on one side, terms without on the other side. So this bit in the middle here, the 2xy squared, I want to stick that over there. Keep the other stuff, so I've got 2x squared y dy dx, plus that will do y dx there. Stick this one over there, so it's minus 2xy squared. Dy dx is a common factor. So finally, dy dx is equal to negative 2x y squared over 2x squared y plus 1. And we were asked to find the gradient at point 1 and negative 2. So we simply, up here, wherever x is, we put in 1, and wherever y is, we put in negative 2. So, at 1 and negative 2, dy dx, which is our gradient, is negative 2 times 1 times negative 2 squared over 2 times 1 squared times negative 2 plus 1. Top line there would be negative 8, bottom line would be negative 4 plus 1, which is negative 3. So the gradient would be 8/3. There we go. Anything you want clarified? Any questions about anything about that? Or do you just need time to get your head around it?
Yeah, time to go.
Time to get your head around it? Yep. Alright, so the key bit is this bit here when you're differentiating. This bit I've got underlined. So when you're differentiating something which has got y in it with respect to x, then you split it up like that. That's the key. All right. 6i then.